You have fallen into Event Horizon with John Michael Godier. In today's episode, John is joined by Dr. James Beacham. Dr. Beacham is a particle physicist, science storyteller, and filmmaker. He's currently a full-time researcher working on the Large Hadron Collider, currently with the Atlas Group of Duke University, based full-time at CERN. He received his PhD at New York University, and before that attended UC Santa Cruz, where he completed a double major in physics and math. His research focuses on searches for new particles and phenomena such as dark matter, dark photons, quantum black holes, and exotic Higgs bosons. He also advocates for future physics experiments such as larger colliders to address the biggest open questions in science. Remember to subscribe to Event Horizon so you never miss an episode.
Dr. James Beacham, welcome back to the program.
Thank you very much for having me. Always a pleasure.
Round two. James, now I have a question. You gave a recent talk that I watched regarding black holes, and I found this particularly interesting because you are not an astrophysicist. You're a particle physicist working at CERN, and you might have a little bit different of a take on black holes than what I usually hear from the astrophysicists. So you have a supermassive black hole, a gigantic monster, and we all know about event horizons, and well, the show's called Event Horizon, and things like that, but you can also have very, very tiny ones that you can create in particle accelerators. And people got really scared when people started talking about, oh, CERN could make a micro black hole. Have you done it? Have we created a micro black hole the size of an atom and it didn't destroy us? Or what stands in the way of creating one if we haven't?
So the answer is very, very obvious, or very, very easy. No, we have not done that at all. So first of all, even if we did that, just to get the obvious thing out of the way for those that don't know, it poses no problem, no danger to humanity in any way whatsoever. Now, I understand that that's possibly a little bit weird for people because, as you pointed out from, science fiction, we think of black holes as these enormous objects that are just like swirling around and sucking in entire planets and stretching out the protagonist until he goes back in time behind his daughter's bookshelf or something like that. But those are for enormous black holes. What a black hole really is, and you're right, I'm not an astrophysicist, but I think all physicists are kind of secretly obsessed with, and sometimes not so secretly obsessed with all of the other branches of physics, because in physics there really are no walls between. There's only windows and doors between the different, sort of sub-realms of physics. And in fact, a lot of what we study at the Large Hadron Collider has direct or, indirect implications on what they learned from astrophysics as well, because it's all part of the same, story. That's part of the same, not story, but, the framework of our understanding of how the universe works. And so it's all connected. So a black hole, though, is really just this. It's any kind of object that satisfies a certain set of properties that are set down and that we understand from Einstein's general relativity. And it's really kind of straightforward. So really what happens is, that gravity as a force, right? It's one of the four, we often refer to as one of the four known fundamental forces of nature. Yeah. And it is, but it's also a bit weird compared to the other three. The other three are the ones you know of as, electromagnetism and something called the weak force, which is, you probably best know, is responsible for things like radioactive decay. It's also the thing that helps keep the sun shining, etc. And then something called the strong force. And this is the one that holds quarks and gluons held together into stable protons and neutrons. And it's good that they're stable because your body is nice and stable. And we're able to have this conversation right now. And so these are the three that we know of. And these are the three that operate on very, very small scales. So the strong force, the weak force, and electromagnetism, they proceed, or the forces arise due to the mechanism of individual particles that feel this force. They exchange other kinds of particles, or so-called force-carrying particles, or vector gauge bosons. And this is the way the force sort of proceeds, right? You can imagine if you and I were on an ice skating rink, we're standing there on ice skates, and I brought an enormous rock with me. I don't know why I brought a big rock, but it's good that I did, because when I throw it toward you, you know that I will move backward a bit on my skates. And then when you catch it, you're also going to, it's very heavy. Ooh, it's going to grab you and you're going to grab it and you're going to move back on your skates as well. So we have, in that sense, exchanged a force carrying particle and something has happened. So that's the way that forces work for three of the known forces of nature. Now, it's still fair to refer to gravity as a force, except the mechanism by which it arises is completely different, a totally different mechanism. And it arises from the fact that, as you know, space is not really nothing. Space is not really empty. Space has a kind of stuffness to it, if you will, not a substance, but a stuffness in the sense that we know that space can in fact bend and flow and stretch. And that seems kind of bizarre because, at least for me as a kid, I always thought of space as just emptiness. Like, what is space? What is nothing? These are kind of weird questions to ask. It's like asking, what is a question? It's one of these strange, almost philosophical questions. But these are the best ones in physics because it really gets at the heart of, of the basics of what our universe is, which is what physics is all about. So when you think about it from that perspective, we recognize that the way that gravity arises is due to the presence of a large amount of stuff, energy or mass density, within a certain volume of space creates a kind of sinkhole in space itself. And it's the famous analogy that everybody uses is, imagine we had a rubber sheet that was stretched tight, and I take a little marble and I flick the marble, it goes in a straight line. But if we put a bowling ball in the middle, now I flick the marble kind of to the side of the bowling ball, from its perspective, it's like it has blinders on and it thinks it's going in a straight line. But from our perspective, we see that it curves around the bowling ball. It's bending around the bowling ball. So that's the way that the force of gravity arises. But if you take that to its logical conclusion, if you pack too much stuff into a fixed volume, space will be bending and in fact flowing toward the center of that volume faster than you could ever possibly travel. And this is, of course, what we refer to as a black hole. So the way you get to a black hole, though, in fact, is just this equation. So, imagine I assume everybody has a textbook on gravity on their bedside table like I do. And so if you just grab that and then you look for the black hole equation, it'll tell you for some given amount of mass, the size of a volume you'd have to pack it in to make a black hole. And it's really straightforward. So if I wanted to make a black hole out of the entire Earth, I need to pack the entire thing into a volume about the size of a blueberry. So that's probably not going to happen anytime soon. So we're quite safe. But I could do with other things. If I wanted to make a black hole out of the sun, I would have to pack the entire thing into a volume that goes around the kind of center part of London. And then if I wanted to make a black hole out of you, I would need to pack you into a volume that's already much, much smaller. I think it's like 1,000th of the diameter of a proton. So you are also safe. We're probably not going to make a black hole out of you. But to finally answer your question, you can also do this with protons themselves. And so if we take, which is what we use at the Large Hadron Collider, right? So the Large Hadron Collider is this 27 kilometer or 17 mile around circular tunnel on the border of France and Switzerland, about 100 meters underground. And in this tunnel, we use superconducting magnets that are colder than outer space to accelerate protons, individual protons, two beams of protons to almost the speed of light in two opposite directions around this ring. And then at 4 points on the ring, we bend these sort of beams together, these protons, and allow them to collide. And so you can also do the calculation for a proton. So if I wanted to make a plain old regular black hole out of two protons just sitting around, a proton has a very, very small mass, and I can use the black hole equation. And if I wanted to make a black hole out of one proton, even two protons, it doesn't matter. I would have to pack those two protons into a volume that's already much, much, much smaller than the Planck length. And given the fact that the Planck length is the smallest physically meaningful distance scale that quantum mechanics allows us to define, a proton is safe. You never make a black hole out of protons. However, the clever amongst the listeners have realized that the reason why we would even think about maybe creating or talk about maybe making a miniature black hole at the Large Hadron Collider is that, like I said earlier, it's not just mass you're packing into a volume to make a black hole or to make gravity work. You can also use energy density. And so, for example, if I take two protons and maybe if I speed them up to extremely high energies, extremely high speeds and kinetic energies, maybe that's enough to make a black hole. It turns out that at the Large Hadron Collider, that is way, way, way too small even to make a classical black hole. And so the reason why anyone ever talked about making a black hole at the Large Hadron Collider ever, even from the beginning, was one of the big things, is because one of the biggest questions, the biggest open questions in science is, why is gravity the way it is? I mentioned earlier that it is a force, but it arises due to a totally different mechanism compared to the other forces of nature. And it's also extremely weak compared to these other forces. Like, it might not seem weak to you because, you're sitting in your chair and you can't, no matter how hard you try, even if you close your eyes and meditate, you can't levitate, you can't fly into the air, you can't beat gravity. But it is extremely weak compared to the other forces. For example, electromagnetism. If you have a refrigerator magnet on your fridge, that is indefinitely beating the force of gravity. It can just sit there forever. So, we know that these other forces are much stronger compared to gravity. And from a physics perspective, again, from a regular person perspective, maybe that doesn't bother you. It's like, well, why should we care about gravity being weaker than the others, man? Well, it's because from a physics perspective, we have no reason, we have no mechanism for to explain why it could be. And that's a bit weird, because we know that throughout the history of physics, certain things that we thought were kind of disconnected phenomena turned out to be very connected phenomena. And so one of the ideas is that far, 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 far back toward the moment of the Big Bang, there was some kind of quantum gravity that existed. Yeah. And this would be some kind of combination, some sort of set of phenomena, extremely high energy phenomena, where these all the forces were kind of on the same footing, if you will. So, the strong force, the weak force, and electromagnetism, these are all kind of within the same realm of strength, if you will. They're all kind of, makes sense that they're sort of distributed the way they are. But then gravity compared to the strong force is something like, if the strong force has a power of 1, then gravity compared to the strong force is like 10 to the power minus 39. So the gravitational pull between two protons is completely negligible. It's there, it's non-zero, but it's completely negligible. So people think about how it is that we could potentially explain why gravity is so weak compared to the other forces. One way is if it's just the way it is, and to really determine, to really definitively make miniature black holes, to understand quantum gravity, we would need a particle collider that reaches an extremely high energy that we currently cannot do with our civilization here on Earth. Or some people came up with some ideas that maybe, in fact, and this energy is, like I referred to earlier, the Planck length. Well, there's similar kind of ultimate values for things like energy as well. And this is the Planck energy. This is the energy at which gravity and quantum mechanics must have something to do with each other. So people started to think, well, wait a minute, one of the ways we could explain that gravity is so weak compared to the other forces of nature is if, in fact, there are other dimensions of space all around you and me everywhere. So at every point in space around us, there might be a tiny curled up loop of dimension and in fact, gravity preferentially leaks into these extra dimensions of space, and you don't feel them, but gravity does. And if we had some kind of special device that could measure gravity in these extra dimensions, we would be able to measure that it is kind of more on the same footing as the other forces of nature. So beyond the fact that that's pretty wild to posit that there are extra dimensions of space everywhere, imperceptible to you and me, what that also would do, it would in fact lower the so-called Planck energy from something, like I said, we'd need some enormous collider that our civilization currently can't build. And it would instead potentially bring the Planck energy, the Planck scale, down to something that was within the realm of the energies of the Large Hadron Collider. So finally, that's why people talked about maybe making hyperdimensional quantum black holes at the Large Hadron Collider, because these would be amazing objects that could teach us about quantum gravity. It would discover extra dimensions of space. It would help us understand what black holes are. We have seen absolutely no evidence of these. And so it doesn't mean that they don't exist. It just means that the length, shall I say, the kind of size of this extra dimension into which gravity could be leaking has to be something very small. So the next time we'll be able to say anything about this, it's still possible that there are extra dimensions of space everywhere around us, but the next time we'll be able to say something about this is probably at the next generation of Hadron Collider machine. That might not happen until, say, the 2080s. So we could be waiting quite a long time. And so, but just to go back to the part about danger or anything like that, there's no danger even if we created one. It'd be fantastic if we saw evidence for these kinds of things in our collider, because these one of the other properties that black holes have is that we know that they have to evaporate. And so I think most people here have heard of things like Hawking radiation. Yeah, it's one of these amazing insights that Stephen Hawking had, that a black hole does not constantly suck in everything forever. At some point, it will, over long enough timescales, it will evaporate. It sort of is constantly kind of radiating in a very, very almost nearly imperceptible way, definitely imperceptible for us here on Earth, imperceptible way, radiating away what it sucks in. And eventually, over long enough timescales, it will radiate away everything and the so-called evaporate. For big black holes, this is an extremely long time. So I think, maybe I'll get it wrong, but something like a solar mass black hole, I think it would take it something like 10 to the power 60 years to finally fully evaporate, given the fact that the Earth is currently, or sorry, the universe is currently about 10 to the power 10 years old. We will not observe one of these anytime soon. But this also applies to any kind of black hole, no matter how big it is. So if you had a tiny, tiny, tiny black hole, 2 protons, again, regular black hole we can't make, but if you had one of these kind of hyperdimensional quantum black holes that we don't see any evidence for, but before the LHC turned on, it's possible they were sitting there in our data waiting for us to discover. Even if that thing existed, you can still calculate how quickly it would evaporate, and would evaporate immediately. It would not stay around long enough to start accreting matter like a regular black hole and suck in the Earth. So that's the long way of saying no.
It's important to remember that gravity says one very simple thing to all of us. I like stuff. And it requires a lot of stuff. And if you've got 2 little tiny particles, it's gone before it has any attraction to other stuff. Again, playing into the idea of how weak gravity is. What is your view as a particle physicist on the existence or non-existence of the graviton?
Ooh, very good question. As a particle physicist, if I were a theorist, I might give you personal views, but as an experimentalist, I'm just going to say that we don't see any evidence for gravitons yet. It's entirely possible that some evidence will come up for them in the future, but the existence of it's one of these things that it's neither a good nor a bad idea. It's an idea, and if it has very specific properties. And one of the things that we've learned with particle physics, it's a very kind of humbling endeavor, because it has taught us over the decades, even far before I was alive or even in the field, it has taught us over the decades that it has a kind of logic to it. There's a kind of mathematical logic to it and some numerical logic, but also it kind of it's going to do what it's going to do, and it doesn't really care about what we as humans want it to do or elegant. So again, one of my favorite books, and arguably I would not be a physicist if it were not for Brian Greene's book from the late 90s called The Elegant Universe. But I also sort of take exception with that, and I like to say that the universe is under no obligation to make its laws seem elegant to humans, because we're just this one sort of ape-like species on this one bizarre planet in the middle of nowhere. There's no reason why we should think of ourselves as special and want the universe to kind of bend to our understanding of the way it works. And what we've learned through physics is that you have certain things that quantum mechanics attaches to particles. It attaches certain properties to them, things like charge and spin and flavor and other kinds of things, and weak isospin. We can get into the kind of more arcane things. And so you can we observe that there are certain values of these parameters, these properties that our universe definitely uses. And there are other possible configurations of particles that could, in principle, exist on paper. And our universe doesn't seem to use these at all. But there's no real reason for them not to. And one of these, for example, is the graviton. So if you found a massless spin 2 particle, and again, you don't need to know the details, but basically if you found a particle is kind of like a photon in the sense that it has a 0 mass, and it had a spin value, which is, again, it's a kind of intrinsic property of the particle. It's related to its internal angular momentum. The value was 2, then that thing would necessarily have to be a graviton based upon what we understand about gravity. And we have seen no evidence of these kinds of things yet. However, just to kind of connect to what we talked about earlier, it's also related to this miniature black hole that we search for at the Large Hadron Collider. We don't see evidence for any evidence for so far. Related to that as well, it depends upon which theory you're talking about extra dimensions of space. Is it like little curled up looped dimensions? Is it kind of membranes or brain theory? Blah blah blah. And if you look at different ones, then you can also come up with a kind of hyperdimensional graviton as well. And that would also help us discover extra dimensions of space and understand quantum gravity. But again, alas, we do not see evidence of gravitons. But if someone does observe something and it has those properties, it has to be a graviton. Yeah. So we don't see any evidence yet, but who knows? Who knows what the future will bring?
Force carrying particles, though, and this gets into elegance because we wish it was elegant, and that we know that there are force carrying particles for the three forces, but gravity, maybe a graviton, something like that. But at the same time, we have the pesky theory of general relativity that we both love, and I love its elegance, by the way. Einstein always just still to this, 40 years after learning what relativity was, I still find it a certain beauty in it.
Agreed.
Problem is, and I think a lot of people get this wrong, they think that scientific theories are theories. No, they're actually descriptions. And general relativity is a beautiful description of how gravity works. It doesn't tell you what it is, though. It just tells you this is what it does. And Newton also in that same grain.
Yeah, I agree.
Can gravity be something, not a force, but something else, a different category? It's a bend in space-time. In other words, there is no force carrying particle there. It's just space-time being warped and bent, as general relativity describes it. Does it even need to be a force?
Yeah, it's a good question. I mean, part of what you're getting at is this, like we were talking about earlier, is this kind of human tendency to want to impose our way of understanding things onto the universe, the way the universe works, right? And we were talking about elegance. I agree with you. I think that I also personally think that the mathematics of general relativity is extremely beautiful, but I also think the mathematics of the standard model of particle physics is quite beautiful. It's just very baroque. It's very strange. It has a weird structure to it, and there's no sort of a priori reason why that structure is the way it is. It's very nicely describes. It extremely accurately describes everything around us at the smallest possible scales. But it's also a bit odd, because as a mathematician, I could write down 1,000 other possible gauge groups, quote unquote, of the standard of standard models of other universes, and our universe doesn't seem to care anything about those at all. So why did it choose this one particular one? It's a bit of an odd question. But it's also possible that at the end of the day, like I said, I think personally it's okay to refer to, and this is sometimes gets into a semantic question for some physicists. I personally think it's okay to refer to gravity as a force, because it's one of the four fundamental ways by which stuff happens in the universe. And there's everything has to be some combination of these four. It's just that, like I said, the mechanism arises due to the force arises due to another mechanism. It's not force carrying particles, except for a graviton, yes. And if we found one, this would also explain quite a bit. But it's okay to refer to it as a force because it still allows things to happen. But the mechanism is, again, something completely different, this kind of warping and bending and curving of space-time. The things that I think are interesting within quantum gravity, as I think we alluded to earlier, we do, in fact, have an extremely good, it's one of the biggest open questions of science. What is quantum gravity? Does it exist? In fact, we have a fantastic theory of it, and several fantastic ideas, but one that's very well advanced, which is, as you know, string theory. And if anyone ever tells you that string theory is dead, they're wrong. It's just that we can't currently test it. And that's two totally different things. If someone tells you that string theory is dead, they're probably trying to get clicks or something like that. It's not. It's a fantastic idea. It makes very precise predictions, except we can't currently test them with the colliders that we have. That means that sometime in the future, we'll be able to directly test this idea. But I think that because of the sort of voracious curiousness of physicists, my theorist colleagues have been thinking about alternative ways to explain quantum gravity over many years. And one of my colleagues in Amsterdam, I think, or somewhere in the Netherlands, Eric Verlinde, maybe he's even been on the show probably, is that, he has this idea that maybe dark matter, for example, is not even there. And in fact, gravity is, and it's just because we have to sort of do a kind of modified version of gravity. Yeah. And it's not sort of old school MOND, if you know what MOND is, modified Newtonian dynamics, which immediately runs into some yes, it immediately runs into some empirical problems. But he thinks that perhaps we do need to modify our understanding of gravity to think that gravity, in fact, as a force, is not really a force, but it's an emergent property of space-time related to the fact that the most fundamental units of stuff in the universe are tiny individual kind of interacting qubits of information that have a kind of pressure, and at that point it kind of gets beyond even my understanding. But this is what we have to do, right? We have to kind of simultaneously keep innovating technologically to eventually be able to test string theory directly. And again, maybe this is 1,000 years in the future, but we're humans, we're going to keep doing this. And then simultaneously, in parallel, we need people to think of new ways and new paradigms, because maybe we're missing something.
That's what we're going to do, because I'm going to invoke the elephant in the room, time, because time also warps and bends and becomes, in Einstein's view, indistinguishable from space. It is space-time. It is, in string theory, a dimension, and sort of looks like a dimension. But on the particle scale with the other forces, do any of them interact with time other than taking time to do stuff? In other words, do they have any relation to time other than the time it takes for two particles to collide? Separate from how gravity seems to interact very, very intimately with time.
Yeah, that's a very good question. And I think we could talk for an entire hour, give some lectures on this topic, because it's really, really fascinating. So you're right to point out that time is a bit of a strange beast. And as you pointed out, Einstein taught us that we cannot consider time as some kind of separate thing, especially when we get to the kind of extremes of the conditions of the universe, extreme gravity, extreme speed. Instead, you have to think about space and time as intimately connected into this thing called space-time, yeah? And so if that's the case, then yes, as you pointed out, time, we know if space can be bent by gravity, then time can be bent by gravity as well. And we know this is the case. In fact, we have evidence for this even, with even around the Earth, correcting for redshift due to the fact that the GPS satellites are so far away from the Earth compared to all the other satellites. If you didn't correct for these kinds of things, then you wind up with inaccuracies in our GPS systems. So we know this kind of thing is real. And we also know that at the smallest possible scale, particles don't really have anything to do with time, except for the fact that we can have thought experiments to think what it would be if we were one of these particles. And this is one of the things that Einstein learned so much about thought experiments. This is something that I love to do as well. Any scientist, any physicist is happy to go along with interesting thought experiments, even if the justification for it or behind the scenes is not so great. It's fun still to have thought experiments. So you can imagine what it would be if you were one of these particles. And we know that the way that time, probably the most important thing the way that time comes in at the very small scales in the universe is that certain particles it's also related to how much mass a particle has. And so, for example, if you're a photon, right, you have to go at something called the speed of light. And that makes sense because photons are light, yeah? And that's only possible because the photon has a zero mass. And we know that this is related also to the fact that, but some particles, they don't have a zero mass. So an electron, for example, if you take an electron and a photon and place them right next to each other, they both in principle have the same size, quote unquote, which is basically zero. I mean, it's, we model them as zero volume particles, as point particles.
Smears across space-time is what they are, just Heisenberg's, smears.
Yeah. Yeah, true. Right, exactly.
And I love it. It's the weirdness of the universe gets even weirder the smaller you go.
Absolutely. No, but so we model these things. Imagine if you had, even if you didn't have to worry about some of the other Heisenberg uncertainty principles, you could only talk about the distance, right? We model these as zero volume points, but the smallest possible, like I said, the smallest physically meaningful distance scale is the Planck length, which is, I guess, 10 to the power minus 35 meters or something like that. I forget what it is, but it's something extremely small. And that's basically what the size is. But they can have different properties. And in fact, they can have different properties of mass. And we know now, for the longest time, as you know, where the property of mass came from was totally bizarre. It was completely unknown. It was just something that was there. And it was always something you could measure. And it was just this number that was always the same for every electron. So it's a number that's put there by nature, but we can't measure it. We can't control it. We can only measure it. But for photons, it's zero. And for the gluon inside your protons and neutrons is also zero. But for other things, it's small but non-zero. For other things, it's actually quite high, right? The Higgs boson has a mass the Higgs boson is even still a point particle, but it has a mass that's something like more than 100 times the mass of a proton, which is not a point particle. It's a big, bulky beast. So we know that these individual particles can have different masses is. And we also know that this is now the reason, the way that the masses of the particles come around, the individual fundamental particles, is because of the existence of this thing called the Higgs field, right? And the Higgs field is this, kind of invisible honey that permeates all of space everywhere, and you don't feel it, but your fundamental particles do. And as they move through the universe, a little bit of their energy of movement is stuck into a point. They're sort of dragged by this honey, and a little bit of it is stuck into a point that we measure as mass. So that's a very good mechanism as to how the concept of mass, or the property of mass, arises. But it also has it's also related to this concept that if you are a particle that has a non-zero mass, you can never go at the speed of light at all. And that's interesting because that means that you do have to experience time as a particle in a certain way that will be, if you were able to grab onto a muon, for example, as it's zipping through, your head, each one of you has about one cosmic ray induced muon going through your head every second. If you were to grab onto one of those things, time would be slowing down for you. From our perspective, we can measure a muon going from above your head to through your head and then down into the earth. But for that muon's perspective, time would be slowing down because it's going at such high speed. This is something that we learned. It has nothing to do with the Higgs field. It has something we learned from Einstein, right? From special relativity. But then if you take this to its logical conclusion, a photon, if you were able to somehow grab onto a photon, time would stop for you. Time does not really exist for you. And this is related to this thing that we talked about earlier, that Einstein pointed out, that space and time have to be thought of as two parts of the same thing, space-time. But if you've ever looked, some people have probably looked at these weird diagrams sometimes online when they're trying to figure out time travel and try to understand it. These kind of space-time diagrams where you have space on one of the axes and time on the other axis. And if you look at what you can do, that's a really good way to think about it, because it points out that space and time, even though they are two parts of the same kind of continuum, if you will, they still have to proceed. Anything in the universe still has to think about what its total space-time budget is, which is fixed based upon these kind of empirical observations that we have. The speed of light. We've never seen anything go faster than the speed of light. Any information or stuff go faster than the speed of light. And so if you have these sort of parameters, then you can think of it like if I'm some object or something in the universe, and I'm spending more of my space-time budget into space, in moving through space, than I have less of that that I can spend in my experience of time. And if I do it the other direction, if I have most of my experience spending my experience in time, I don't have as much budget to go in space. So you and I, we're basically time-like beings, right? We're sitting around and time is moving in at a rate of 1 second per second all the time, and we can't all the time, and we can't control that. We can't change that very much at all. That means that we're also not moving very much through space. We're not using much of our space budget at all, which kind of makes sense. We're stuck on this planet, right? We don't have warp drives. We can't move like some of these people say that UFOs move, with warp drives. So this is a way to think about it. I guess this is sort of the roundabout way of answering your question. Is that when we think about time at the smallest possible scales, the individual particles themselves can't really affect time. It's just that time is something that they have to deal with in certain ways, and that if you were to somehow anthropomorphize one of these particles and experience or try to imagine grabbing a ride on a muon, you would start experiencing time in a very different way than what you and I do.
Yes, and again, that hammers home what we were talking about, that time is intimately linked. Yet we know, as far as I'm aware, we know less about time and what time actually is than we do gravity. We just know that the clock is ticking, and it ticks at different rates depending on what you're doing. And it's
absolutely,
it's just amazing.
It's so strange. It's so strange. And it honestly, probably it's the same for you, John. It's like, it never gets boring to me. Like I could think about, I could spend 10 lifetimes studying time, and it never gets boring at all. Even thinking the same.
I got another one for you.
Please, go ahead.
Okay. As a physicist, are there certain things that when you look at the math and you look at the universe that just freak you out? And one of them for me is when the equations start spitting out infinity. And Einstein's good for this. And it's like, how could that realistically be? Come on, infinite energy, and things like that. What are some of the good ones that you've come across?
Oh, boy. So I don't know if, okay. I don't know if anything really freaks me out or that kind of surprises me or kind of spooks me or anything like that. But there are certain things. I take it from another perspective, right? As an experimentalist, right? I I've been to the state of Missouri. I love St. Louis. I love all these I love it, but I'm not from Missouri. But in this case, I'm the Missouri man. Show me. Show me. You have to show me the data, show me the evidence, and then I'll start to assent to the reality of something. And so if so when I see things in theories and in mathematics that spit out bizarre things, I don't think, oh no, that's crazy. Instead, I think that's probably not real. And the ones for me that I love are, for example, like you pointed out, some of the infinities and bizarre things that you get with general relativity. Yeah, so we can go back to black holes, right? One of the things that we currently don't know, and it's related to all the same, it's basically the same question we're asking from different directions. Yeah, we're approaching the question from different directions. So what's at the center of a black hole? If a black hole continuously sucks stuff in until eventually 10 to the power 60 years from now will eventually evaporate, where does all that stuff go? And like, how could it suck in entire stars? Where does the stuff for the star go? And if you look at the mathematics of the equation of general relativity, there, at the center of a black hole sits a point that just doesn't make any sense at all, which is the singularity. And no, we're not talking about the silly kind of social media singularity, or these kinds of guys write books about, right, that are very silly. But we're talking about an actual singularity, meaning a point that is of infinite curvature and zero volume. Like, I don't even know what these things mean, physically mean, and I'm a physicist, right? So these are the kind of things that when I see those things, I don't think necessarily that they're scary. I just think the universe probably doesn't actually use that, right? And this is one of the ways, the reason why I think of it that way is because, as you know, throughout the history of physics, usually when your math tells you something like that just doesn't make any logical sense, it's kind of the universe's way of telling us to think harder about our theory, about our description. And, of course, to put a fine point on what you said earlier, it's totally true. It's important to remind people that when we use the word theory in science, we actually mean something, especially in physics, we mean something different than what people use about, in a kind of colloquial sense of theory. It's like, whoa, I think that, JFK was shot by 10 different people at the same time. That's just your theory, man. Well, no, that's not the way that we use the word theory in science. In science, a theory is a well-described, is a well-developed mathematical description of something that either does or does not match our data. And if it does match our data, it gets to be the current best understanding of the way the universe works. And that's where we find ourselves with both general relativity, the way things move at extremely large scales, and then also the standard model of particle physics based upon quantum field theory that describes how everything works at the smallest possible scales. So these kind of things, when I see these kinds of infinities, these sorts of bizarre things, I always get freaked out. But the one freaked out from the sense that, like, the universe probably doesn't use this. One of the things that I love also is if you look at some of the kind of naive ways of combining just plain vanilla quantum field theory and plain vanilla general relativity. If you try to quantize general relativity, then sometimes you get probabilities that are greater than one. That's a great one for me, because I have no idea what that means.
Yeah, and the big question, and you probably knew exactly where I was going, it was the disparity, the missing puzzle piece between general relativity and quantum mechanics, and that it just breaks down. Relativity breaks down.
It does.
At the level of the tiny. And quantum theory, which actually is a more successful theory than general relativity, which is saying a whole lot, but it is. And in fact, it could be one of our best theories in all of science, ultimately, because it really, really does a nice job, but it doesn't quite work with, it scales up a little bit. You can have quantum effects in our world, but doesn't really go the other way around, it seems. Do you think this is simply a matter of a missing puzzle piece? In other words, for the longest time, a couple hundred years, we went on Newton. We went on Isaac Newton's idea, but then we started seeing discrepancies, and that led to relativity. Do you think that's the case, that we just don't have a fine enough point on one of either theories, or do you think that we need a linking theory between the two?
I think that probably there is going to be some eventually there will be some coherent and testable theory of quantum gravity that makes this connection. And like I said, again, I don't advocate for one theory over another, but I do think that string theory, for all of the kind of the kind of derision that it gets from people that are not in the field, which is totally unwarranted from a physicist perspective, string theory is extremely good. Like, it actually does make this connection. It was sort of the missing piece that we would need, because what it does is kind of related. It's not the same thing, but it's related to this notion that we said earlier, there could be extra dimensions of space. Imagine that if you look at smaller and smaller and smaller scales of a tiny particle, we said that, for example, an electron is a point particle, is a zero volume point. But in fact, maybe if we were to had some kind of device that could look, quote unquote, and this device would be an enormous particle collider, it could look at the distance scale of an electron down the length of the kind of Planck length, we would in fact see that an electron is not a point particle, but in fact is a tiny curled up loop of, string. These are kind of strings that they refer to. And once you posit that, just extra substructure within things that we think of as having no substructure, it immediately solves all the problems. And so I think the string theory is potentially the missing piece that that we need. Like we said earlier, it's just currently not directly testable in a way that we would need to satisfy the rigors of the field, because as you pointed out, quantum mechanics, quantum field theory, these are, and I agree with you. I mean, it's shocking sometimes how well this describes reality. And if we think about the most fundamental level of everything, that's the smallest level. Yeah, that's the way the universe works. The universe is quantum, full stop. And that's a bit strange because, the precise predictions that it makes, we have basically, all the ones that we've been able to test so far have been spot on. So it is quite alarmingly good. So there's probably, quantum mechanics is probably not wrong. By the same token, though, general relativity seems also to not be wrong. I mean, as you pointed out, it works at this one level. It was the thing that supplanted Newton, but it also, like you said, you can't scale it down. You can't actually see if it's applicable all the way down to the level of these individual particles. We don't have any, evidence of how that could work. And that's a bit of a puzzle. At this point, we sort of start getting into kind of philosophical questions too, because some people also would point out, it's like, you guys you physicists use physicists, something. I'm from Pennsylvania. No, you physicists, why would you think that again, it's this sort of like human hubristic thing. Why would you think that the universe would satisfy your desire to have a kind of elegant connection between these things? And that's a fine point, and it's entirely possible. At the end of the day, maybe we have these two extremely good theories, and they just describe completely different realms of physics almost perfectly, but they just don't go together. But that's a bit weird, and I would say it's weird not from an elegance perspective, which again, as a person with an artistic practice, I love beauty and elegance and design and things like that too. But the universe doesn't need that doesn't need arguments from elegance or beauty. Instead, you just need arguments from stuff that's happened before, for the following reason. Like we talked about earlier, history of physics is filled with things that we thought were disconnected phenomena, and in fact turned out to be intimately connected, like we said, space and time. Or, for example, in my field, in particle physics, all the forces. So if you go back to the mid 1800s, right, you had electricity and you had magnetism, and they were described separately. It's like, oh yeah, they have their own separate things. Then you get farther and farther along, you realize, wait a minute, these are in fact two parts of the same fundamental force known as electromagnetism. You can't think of them as two different things anymore. And then we also, once we recognize that things like the weak force and the strong force existed as well, it turns out that if you go to high enough energy scales that we can only access in particle colliders, the electromagnetic force and the weak force are actually two parts of the same force called the electroweak force. We know this for a fact. And we also suspect the same thing is the case with the electroweak force and the strong force. That's also beyond what we currently can test directly at particle physics colliders that we can do on Earth. So that, from that perspective, it sort of just makes logical, kind of historical sense that this would also happen with gravity. At the end of the day, maybe it's completely wrong. Maybe we're totally wrong. And again, any good physicist is happy to be proven wrong. And again, I'm not actually advocating for one thing or the other. I'm, show me the evidence and I'm happy to assent to the reality of this thing. But until I have evidence for the thing, I'm not going to assent to the reality of it. And if that's the case, then there could be, and like I said, things like string theory or some of the other more, the other arcane ones like loop quantum gravity, other kinds of ideas, these postulate that at some point far back toward the moment of the Big Bang, there could have been one sort of like grand unified field theory where all the forces were all kind of on the same footing. And if this is the case, this is not an argument from elegance necessarily. It's just an argument from this has happened before in the history of physics. So it's a good idea it's a well-motivated idea to pursue this line of thinking, this line of experimental research to either verify it or rule it out.
You could almost say it's like, we could call it, we'll coin a phrase, the Notre Dame effect. In other words, we all, I went in there 25 years ago and I looked at this dark cathedral with, very beautiful, and weighted in history. But who'd have thought it would have cleaned up like that after the restoration? It's like, I didn't expect this. And maybe theories do that too, where, they look messy and some of them old and some of them new. And then all of a sudden, once you see the finished product, it's like, I didn't expect that.
Yeah.
And you end up with something completely new. Your paradigm changes, basically, is what I'm saying.
Absolutely. And that's why we find ourselves in a very strange place, as you know, in physics right now, is that honestly, we have big open questions. We have enormous open questions. And in fact, one of the biggest ones, like we've been talking about, quantum gravity, in fact, we kind of know how to answer that question. It's just that we're at this weird place where the math and the theory is so far ahead of what we technologically can do that it creates this, it's almost this bizarre, like, gap in the head of every physicist. We're like, I really wish that we had the civilization capabilities to build James's particle collider that he wants to build around the outer orbit of Neptune to reach the Planck energy, to make miniature black holes and to figure out what quantum gravity is. But we can't do that right now. So what else do we do? So we're kind of stuck at this point where we honestly could have already theoretically gone through this paradigm change. And again, this is another version of, I think, what is that even back in the day, like in the 60s and 70s and the 80s, when people were developing string theory as an idea, it wasn't clear. And in fact, at the time, they were all kind of like looking in different directions, and somebody's like, no, mine's better, and no, mine's better, and this one is better, and this one is better. And then people like Ed Witten finally came together and said, actually, you guys are all talking about the same thing secretly. And it was like, oh, hell yeah. And that's when it kind of, like in the late 90s, in the mid 90s, late 90s, is when string theory finally got around to recognize that all of its practitioners were kind of talking about the same basic underlying theory. And again, at the end of the day, this is a fantastic thing to do. It's a wonderful direction to do your theoretical research and your calculations. But physics is an experimental science. And until we can test this directly, it will still remain in the realm of an extremely good, well-motivated, elegant, dare I say, elegant idea that we currently can't test. So I don't know. It's impossible that what you're saying, we might have already gone through the paradigm shift in theory, and we won't be able to go through the paradigm shift in experiment for, I don't know, centuries. Not sure.
This would scare most physicists, and if it scares you, I'm happy to do it. That which science cannot know. Eventually you get to the point where no one can test a certain idea. And some have said that about string theory. Now, I have not thrown string theory into the wastebasket either. I think it's a good idea. But again, how do you test it?
Yeah.
And I think a lot of people get a motive and they're like, oh, yeah, the scientists were wrong. Well, wait a minute. No, we're just trying to describe something. And in the case of string theory, do you think we eventually hit a brick wall? And you could say this about any area of science, actually, where it becomes unknowable. And the universe just simply does not guarantee that you can ever fully understand it. What is the limit of science?
Yeah, this is a good question, and it's wonderful food for thought. I find myself in different realms of different ways of answering the question based upon mood and context, and also what who I'm talking to, and also what it is that we're trying to understand, right? And because I'm a hardcore rationalist, hardcore imperialist, right? Empiricist, not imperialist. I'm extremely anti-imperialist.
No, but not imperialist. Bad word.
No, I'm a hardcore empiricist, and I think that when we are, there are always going to be limitations, I think, to our human understanding. But when I say those words, I do not mean that in a kind of religious way or even a spiritual way, because I'm an atheist. I mean, atheism is the default condition of humankind, and I'm just a kind of natural, normal sort of logic seeking human that is sitting around thinking things about the universe. So when I say that, it's not coming from a kind of spiritual or religious place, but it's just that we as humans, we know for a fact, based upon our experiments and based upon our understanding of the universe, that our human abilities to interact with the universe itself are extremely limited, right? We know this. We know for a fact that, and like I said, you have about one cosmic ray muon passing through your head every second. You also have about 65 billion neutrinos from the sun going through your thumb every second. You have about a billion particles of dark matter flowing through your body every second. And your eye, much to the chagrin of, some of these kinds of young Earth creationists who are like, well, look at the human eye. It's so perfect. It could never have evolved on its own. Actually, it's evolved millions of times on its own in multiple different contexts. And also, it sucks.
And independently.
Yeah, and it has.
And independently. Trust me, our eye sucks compared to a trilobite.
Our eyes also suck. They're terrible experimental apparatuses because we can only see a tiny, tiny, narrow range of the electromagnetic spectrum, which we know is enormous beyond that, right? So if someone tries to tell you that the eye is well designed, it's not. It's just this. So we know, and you know where I'm going with this, right? Is that we as humans, for me, I think it's a powerful position to be in because it's humble, because it's acknowledging our human limitations to recognize that there are only certain things that our five senses is the only way that we have to take in new information about the world. Of course, we have technology.
No, but there's something. Yeah, the technology lets you do things like pick up a radio, though, and because you have an indication. You have an indication that there's something there in that part of the spectrum that you can pick up. So you build a radio to figure it out.
Correct.
But what if things that might exist that have no way we could even measure them? In other words, the only reason we know about dark matter is its gravity. Mm-hmm. It's all we know. But basically, there are a few other little hints here and there. But fundamentally, we the only reason we know about it is that we saw galaxies behaving in a way that gravity wasn't consistent with. And that brought up things like Mond, and those sorts of things. But had gravity been completely non-interactive, instead of a WIMP, it's a nothing and doesn't interact at all, yet it exists. Mm-hmm. Could that be a big problem with science, is the unmeasurable, something that just simply gives no indication of anything other than very weird peripheral hints? Like, I don't know, the fine-tuning problem might be a hint that there might be things going on that we just have no ability to measure. The unmeasurable, how big of a problem? Does that keep you up at night?
Yeah, I mean, again, I'm sort of a hardcore naturalist in this perspective, is that I think that if something is literally unmeasurable, then it probably is not real. And I think that this is not a problem for me. And I know that sounds kind of hardcore sometimes, but I say it from the perspective of, again, what we have as humans is we have, we pointed out technology, and I wasn't saying that our five senses are the only literal ways to understand the universe. We have been clever enough as a species to design implements and technology that can extend our five senses beyond what we can directly interact with, and we can indirectly see things, and we can see, quote unquote, we can indirectly detect things, and we can indirectly demonstrate definitively that certain things are real. So as you pointed out, dark matter, we've never detected a single particle of dark matter ever. We know for a fact that something is up in the sky due to the way that galaxies are moving, as you pointed out. And that's just empirically true. There's no ambiguity there. There's something up that we currently can't explain. One of the good explanations for that is if you just postulate there's more stuff in galaxies than what we can see with our telescopes. And if it doesn't interact by electromagnetism, then if it's not light, then it's dark. And so then you go through the different possibilities as how you could possibly detect this particle, et cetera. At the end of the day, though, if, as you pointed out, or as you sort of observed, if dark matter only interacts gravitationally, we're kind of screwed to demonstrate what it is empirically and to discover if it is a particle. There's a limitation there to our current human understanding. However, I am also the kind of, even though I'm a hardcore rationalist and naturalist, I'm also a hardcore optimist, because there have definitely been times in the past when somebody's like, well, we'll never know the answer to that. And then somebody eventually came along and came up with a way to answer a question. So this is related to the things you're talking about here, is that I like to be both the very clear naturalist and rationalist, but also the optimist. I would never be so hubristic as to think that someone in the future would not be able to come up with a way to test some of these things. So string theory, like we've been talking about, I mean, it's just it's just wrong to say that the string theory is dead, and it's wrong to say that string theorists are wrong. This is this is just not accurate in any way. It's just something we currently can't test, and it's okay for things to be currently unknown. There's lots of unknown things in science. It should it can keep scientists up at night, but it doesn't need to cause us undue anxiety and stress because we can't currently answer it right now. And honestly, it's a bit weird to me, even though as a person, on a personal level, I would love to be alive when we figure out what dark matter is and quantum gravity. But scientific discoveries are not more important just because they happen within my lifetime, right? I wasn't alive when the electron was discovered. That doesn't make its discovery any less interesting to me. So dark matter, if it's discovered after I'm dead, that's still interesting. That's fascinating. I just won't be around to figure it out. But the wheel of scientific inquiry will still be able to pick it up, because this is kind of what we're getting at deep down underneath. Science is, it's not a list of facts. It's not a guy, a tall white man in a lab coat telling you what to do. It's a process. It's a method by which we as humans, the only one that we know of, that allows us to ask and answer questions about the way the universe works, to arrive at robust, repeatable, reliable information and current conclusions about the way the universe works, our best understanding right now. And it's always updatable with new information. It's always subject to refinement, as you pointed out several times in this discussion. And so if that's the sense, science, there's nothing that science can't address. Everything can be addressed by science. It's just that maybe there's certain things that can't be, certain theories that can't be directly tested right this moment. And those things are the ones that I think bother a lot of people when they get the wrong impression as to what science is. It's like, well, science. So, if this occasionally happens to me when I'm giving public talks. It's like, well, science doesn't have all the answers. Science never said it had all the answers. Science isn't really about answers. It's a process. And so if that's the case, science will never end. There's no end to science. And this is related to what you pointed out. For example, the fine tuning problem, right? I mean, this is another thing that I love to think about, a lot of us love to think about, is this concept of the multiverse, right? Is that our universe seems to be filled with a lot of these kind of magic numbers, right? These are just values of constants of nature that are just some number that we have no real reason as to why that number is the way it is. The gravitational constant, the charge of the electron, the vacuum expectation value of the Higgs field, right? These are just numbers, but there's no a priori reason why those numbers are the way they are. But it's very good that they are what they are, because it makes our universe what it is now, and if those values had been something very different in the early universe, our universe would have been a totally different place as it expanded. Maybe it wouldn't even expand at all. We would not be here to have this conversation. So, and that bothers a lot of physicists. It's like, well, okay, if these numbers are, then how did they get there? Like why and how did, what's the mechanism by which these numbers are, arrived at what these values, to these very friendly values? This is the kind of anthropic argument, right? And so some people take that in the wrong direction. They're like, oh, well, that means that our universe was fine-tuned. I know that's not what you were saying, but some people, if they wanted to extrapolate, they're like, it's fine-tuned by a higher intelligence. Record scratch. That's not what anybody said. Scientifically, what it means is that it's a statistical statement. Yeah. So one of the ways that you could potentially, one of the potential mechanisms by which our universe could arrive at these extremely friendly, very nice magic numbers. And I use the word magic. It's not actually magic. That's poetry, by the way. Is if we know that our universe loves statistical distributions, so the average resting heart rate of everyone listening to this will follow some kind of Gaussian or normal distribution. If you stand on a street corner, the rate at which cars will pass you will follow some kind of Poisson distribution. Our universe loves these statistical distributions. So maybe behind the scenes, in fact, in the sort of whatever you want to refer to it as a kind of multiverse landscape, it's entirely possible that our universe is not the only universe. There could, in fact, be an almost infinite number, or some very large number of, almost infinite doesn't really mean anything, a very large number of other universes in a kind of multiverse landscape. And these values of the constants of nature were taken off of some statistical distribution, and they're different values in other universes. And most of those are completely boring, like we said, but at least one of them had to turn into something like ours. So that's not a religious statement. It's not a spiritual statement. It's a statistical statement. And if that's the case, then you start asking, getting back to what you're talking about, is where is the evidence, and also how can we test this idea? And that's, of course, the part where we get to the edges, which is exactly what we're talking about. Is it possible for something to be just unmeasurable? What does that say about science? At the current moment, I don't even know in principle how someone is supposed to test the existence of, design an experiment to test the existence of other multiverses. Yes, we have sort of, people try to make arguments from, the cosmic microwave background radiation. You can see kind of, sort of poles in there of cold spots and things like that. Okay, that's fine. These are sort of circumstantial ideas. There's nothing wrong with that. But if you wanted to design an experiment to test this idea, I have no idea how you would do that right now. That does not mean that someone in the future will not come up with the way to do it. It just means that it's not currently testable. So this, to me, is something. This is the space that we have to occupy as scientifically minded people. We can approach basically everything in the universe with a scientific mindset, and we have to remind ourselves, though, that an idea is an idea is an idea, and I will not assent to the reality of something unless and until I find direct evidence for it in a scientific way. It doesn't mean your idea is wrong, and it doesn't mean that it's bad. It just means that it's currently not supported by evidence. And that's okay. That's a different statement. But of course, the problem is that, as you pointed out, people get emotive and they want more than that. They want, we have this human brain that evolved, our species evolved in this very friendly way. We did not evolve at the quantum level, so we do not, quote unquote, understand quantum mechanics. We did not evolve at the level of, neutron stars, bending the fabric of space-time. We evolved in this very friendly thing. And so we have, our entire species history has been in this extremely friendly, lovely realm where things sort of made sense and we had emotions to connect with each other. But the universe doesn't care about our emotions. I mean, it's in a sense that there's not some universe outside of who we are. You know what I mean? I mean, as you know, we are actually embedded within the universe. And kind of going back to, Wheeler, one of my favorite thinkers in this realm, is that, we as humans, in a sense, we are the method by which the universe asks questions about itself. Yes, we are limited devices. We are limited experimental devices. But we have done a remarkably good job building these kind of technological implements to try to start to understand the universe in realms that we can't directly interact with. So for me, there's not really anything that's unanswerable or unmeasurable for certain things, unless if it's not a well posed or not well posable question, then it's in the realm of poetry or religion or kind of speculation. And these things are they are what they are. They're human endeavors. But if we're talking about the physical reality of the world, then all that stuff can be addressed with science.
I absolutely love Wheeler's ideas, and I think about them often, right or wrong, and often we don't even know. Things like the one electron theory and things like that.
Yeah.
But at the same time, it would please me greatly. I don't need an end to science before I depart from this world, but it would be funny if we did get an alien signal and after much deciphering and many years of trying to figure out what it says, it's a million years more advanced civilization asking us, so
that would be amazing.
You guys think there's anything to string theory? They don't know either. What do you guys think there's anything to string theory? They don't know either. Now, James, I use that as a segue. That would be amazing, and I would love that universe. Anyway, you attended recently. My last question for you is the Soul Conference. And speaking of things like open-mindedness and thinking outside the box, thoughts on the UFO UAP phenomenon after that conference? What do you think, listening to those talks?
Yeah, so the Soul Symposium was really fascinating. And so, I got the invitation from the founders of the Soul Foundation, from Peter Skafish and
Gary Nolan.
Gary Nolan, yes, love Gary. So, I got the invitation through, I was connected up with them through a fellow, kind of thinker and science-minded person that I spoke at a different event with. So I've spoken at events with, say, Avi Loeb. I know Avi for a few years now, and people like that. And as the reason that I'm even here, right, is because I'm not just my day job is, particle physicist at the Large Hadron Collider, looking for dark matter, things like this. But I also like to think about the edges of science. I like to think about, as we've just talked about right now. I mean, this stuff is fascinating to me, the kind of gray areas, the sort of fringes. But it's also important to be clear about what is and is not science within these realms. And so I think that the Soul Foundation is admirable, to me. And it's one of the reasons why I accepted the invitation is because, as we were talking about earlier, we kind of touched upon this notion of faith and belief and, spirituality, blah, blah, blah. We didn't go into too much detail about it, but, these kinds of things, to me, to me, science has nothing to do with belief. And if someone says that science is just another belief system, they're probably operating with not a full understanding of what science is. Because with belief, you always have a choice. This is the way that I see it. With belief, you can always choose something. If somebody says, says like, well, I think that there's an invisible green leprechaun that lives up in that tree, and you can choose to believe what this person says or not. And as a result of that, there's very different way, science proceeds in a very different way with a different set of principles when we start to posit, questions and try to answer them. And so it's very different from faith, where faith within most religions, faith is this concept where you're required to assent to the reality of something, specifically in the absence of evidence for it. Because if you had evidence for it, you would not need faith. And a lot of religious traditions that are major ones that we're exposed to, they require you to have faith. So that's completely opposite of what science is, right? Like I said, what we were talking about earlier, right? In science, we don't assent to the reality of something until and unless we have evidence for it. So the problem, so that's just a long way of saying that, I have talked to people over the years who are very much into the kind of UFO and UAP realm, and people that always ask me about alien civilizations, typically not in the sense of like little green men or gray men coming in the middle of the night to abduct you in your room or something like that, but more about, you think there's like extraterrestrial intelligence out there. And extraterrestrial intelligence, I think, is, like I said, anything can be addressed with science. I think that ET hypothesis can be addressed with science. And this is the realm of, say, SETI and, so shout out to Bill Diamond and Jill Tarter and these kinds of people. But then simultaneously, I do talk to a lot of people who, ask me about UFOs. Do you think UFOs are real? And most of the time, the people in that realm, a lot of them, I'm not going to say most or not, because I haven't really talked to everyone, but a lot of people in that realm, they already have a kind of conclusion in their mind, and now they're just waiting for some kind of specific evidence for it. And that's kind of the opposite of the way science works, the way that we just talked about, right?
Preconceived notion.
Yeah, exactly.
Yeah. And you work towards that. That's not logic.
Yeah.
It isn't logic to try to work towards what you've already concluded. And I think that's a problem there. But at the same time, I have to say, it's worth studying and seeing what might be there, because there is weird stuff there.
Oh yeah. Sorry, I'm getting kind of long-winded here, but this is kind of a long way of saying that I recognize that what the Sol Foundation is trying to do is admirable, because it's entirely true. It should not be, shall we say, controversial at all for any scientist. There are definitely unexplained aerial phenomena. They do exist. The thing is that there are lots of unexplained things in science, and that's okay. It's like we just talked about. There are certain things that are unexplained in science. It does not mean that the conclusions that a lot of people in the realm jump to are well motivated, and the things that really don't follow from that. And so I think that many people will disagree with me in here, but for me, the extraterrestrial hypothesis and UAP kind of deserve to be treated as two different fields, because I don't think that the existence of something unexplained in the air, that does not directly imply the extraterrestrial hypothesis. It does not directly imply too many of the things that a lot of people in the realm jump to, say like the supernatural or like the paranormal. And keep in mind that the supernatural doesn't exist, because if it did, it would be natural. And so these kinds of things are too often jumped to by people that are in the realm. But I really liked the fact that the Sol Foundation was taking a different tack on this. They're saying, listen, there are certain things that are unexplained. And they have a lot of contacts of people in, say, military or, ex-military and intelligence sources that I don't have access to as a scientist. And they tell me that there's lots of good information and lots of hidden information within government archives. And that's fine. I'm not going to dispute that. But I also can't use that as scientific evidence for something beyond what we can just see with our eyes. You know what I mean? This is a long way of saying that I agree with you. UAP, just like anything else, can be studied with a scientific lens. And I found the Sol Symposium really interesting because, like I said, they had an interesting group. They had an interesting cross section of people thinking about this set of phenomena from different perspectives. One, for example, they had the real sort of people. In fact, I think they refer to them as experiencers. People there, not everyone, but several people there that I talked to, they actually do have personal experiences that they say that either they were abducted by some kind of alien spacecraft or alien beings, or they saw strange visions that they couldn't explain over, weeks and months and years or something like that. or they had they had direct evidence or something, or so these are experiencers. There were certain of these people that were in that conference, but by the same token, there were a large number of people who were there to try to approach the kind of unexplained part from a more kind of empirical lens. And I liked that. That's why, eventually that's why I accepted the invitation, because they invited me as a kind of, as an outside scientist. If I were, ostensibly the reason was to bring somebody from outside the realm, and under the assumption that some of the behaviors of some of the reported UAP over the years were, they represented real craft. What could physically account for the behaviors of those craft? And so there's a lot of assumptions there. In my talk, in fact, I just made it clear that I currently don't think that some of these assumptions are justified. I think that we have lots of reports of things, of UFOs or UAPs over the years, but they, fully 95% of them have been and can be explained by natural phenomena. And just because we have 5% that cannot be, that does not logically necessarily lead to some of the conclusions that a lot of people like to make. And it's like, extraterrestrials or, or technology beyond, the realm of the earth. These things just don't follow from that scientifically. It's like we have something that's unexplained. Let's try to explain it rather than jump to, this is alien technology. And so that was my role there, as I dove into some of the this sort of well-known UAP sightings. The one that I used as one of my main test cases was this so-called Nimitz sighting. So there was the USS Nimitz carrier group that was off the coast of San Francisco.
David Fravor.
Yeah, exactly. Off the coast of Southern California back in 2004, 20 years ago, almost to the month. And over several weeks, a lot of the personnel there were reporting seeing a lot of unexplained things. And in fact, some of the, like Fravor and some of these people and some of the other pilots, they saw what they referred to as an enormous white tic tac that was behaving in bizarre ways. And so, like I said earlier, I don't accept the assumption, because I don't have anything other than these kinds of firsthand experiences, right? The people that are saying things. But unfortunately, even if you have a preponderance of people saying things with firsthand accounts and eyewitness accounts, these unfortunately do not amount to robust data that we can use to then conclude something directly about these phenomena. They just don't.
Yeah, but they do accomplish one thing. And this is where I say, okay, pay attention. They tell you there's something to look for. There's something to try to collect data on and get a data set that isn't classified.
Absolutely.
Because the government could have whatever. I mean, they could have the Roswell UFO in a warehouse and a body in a freezer.
Right.
But if they're not going to show it to you, it doesn't do anything.
Exactly.
Might as well be confetti, frankly. But if you can get, and this is why I support Avi Loeb and the Galileo Project, go get a data set. Get good instruments out there with calibration and known methods and all this. Get a data set and let's see what they find.
Yep.
If it's nothing, then we know. If it's something, then we got a lot of questions. So I think the open mind is the most important thing in this issue. Wouldn't you agree?
I agree. And, I think that when they finally post the talks online, they said they were going to post the talks eventually. I think you'll see a lot of similarities in the way we think with my talk, because I tried to do that. I mean, again, I like any physicist, I'm happy to go through thought experiments. And I did. It's like, okay, under the assumption that there was some bizarre, 50-foot long tic tac that went from 80,000 foot altitude down to 50 feet within like 2 seconds. What could possibly do that? And it's fun to go through the physical, the thought experiment. But at the end of the day, these things, they do. Yeah, I agree with you. It's fine for people to, if you have a preponderance of people saying that they have had direct experiences and eyewitness accounts, that's fine. And it can say, okay, well, let's take a look at this in more detail. But until and unless we have repeatable, robust, reliable, big visual data for these things, there's very little we can do scientifically. And that was basically my point as well. And, like you pointed out, I have the same view as this. If there are hidden things within government archives that they're not showing us, they're not showing this, and I can't do anything with that. And I also can't assent to that. If somebody, just because somebody who, and I shouldn't say just because I don't dismiss anybody's, accounts, but to be very clear, I'm not dismissing people's firsthand experiences. Even some of the people that were experiencers there at the symposium, they had real experiences. The problem, though, is that I have also had extremely real experiences that were like dreams that I thought at the time seemed extremely real. If I want to take that from an extrapolation from a kind of personal experience to some kind of objective claim about physical reality, the criteria become different. And again, it's not to dismiss. In fact, I honor all these people's experiences. But when we try to take those from the kind of firsthand eyewitness experience into some kind of objective claim about reality, a physical reality, those criteria are going to be very difficult to satisfy until and unless we have big visual data. I mean, it's also totally, it's completely valid. It's the same kind of objection that many people within the UAP field have heard many, many times, and they're probably bored to tears of hearing about it. But the problem they keep hearing about it is that it's still valid, is that if there are thousands of UAP reports, even like every year, and some 5% of them cannot be explained, and some percentage of those are seen by multiple people, then where are the big obvious videos and photos? Like there's 7 billion smartphones on the planet, right? And so the lack of this kind of big data, and it's really it's not valid to say that everyone who sees a UAP is just too stunned and is too shocked to pull out their phone. I mean, everyone pulls out their phones to take photos of everything all the time. It's like it's a well-oiled human response at this point. So the absence of this kind of data is in fact surprising. So, and maybe there's something going on again, I don't really know how to explain why that would happen, except for maybe that those things can have natural explanations instead. Or no, there's also psychological effects that, lots of different waves of reportings have been explained by, or at least to the satisfaction of many scientifically minded people. I don't think these things are contradictory. I think at the end of the day, it's okay for us to say, number one, the most important letter in that acronym is U, which is unexplained. And there's lots of things that are unexplained or unidentified, right? Unidentified, anomalous phenomena. And simultaneously, it's okay for us to say, I can't assent to the reality of this being anything other than an unidentified phenomenon until I see some kind of big, obvious visual evidence for it. That's great. If we want to collect that, fantastic. And I will be the first person. In fact, every debunker, one of these people that, make these videos online, if you had big, obvious evidence that was repeated by 1,000 people that saw it all at the same time, they would immediately, they're like, yep, this is it. This is the real thing. You go through run it through the different filters to try to see if it was, these are all 1,000 of the same deep fake. And if they're not, then, the debunkers would be on your side too. So that's what I really liked about the Sol Foundation. Another thing that the symposium was really interested in is that they approached the UAP idea, or the sort of realm, not only from the kind of hard physical science perspective, but also on the first day of this symposium. It was fascinating because there was a talk from, I forgot the gentleman's name, but he was fantastic. It was and he's going to be angry at me for forgetting his name, but he was a professor who talks about the kind of sociology and anthropology of UAP sightings and UFO sightings throughout history, specifically in the context of, say, what they have meant to, say, African-American society or cultures throughout, say, the last 100 years. And it was fascinating to talk about how, for example, in Black culture and Black music from like Parliament Funkadelic and, like Outcast ATLians, about how UFO sightings said a lot.
Never thought I would hear never thought I would hear a P-Funk reference on my show ever. But that was they don't make music like that anymore.
They do not. Well, in fact, by the way, George Clinton is still doing amazing things. He's just kind of behind the scenes these days.
Yeah, it was George Clinton and Bootsy Collins. Oh, yeah. And anyway, I'm sorry. You sent me off on a tangent.
No, we can.
I love music.
We can geek out on funk all we want. So, for example, this is my recommendation. Go and listen to the song "King Kunta" by Kendrick Lamar, one of arguably the best hip hop artist working today.
Yeah,
maybe of all time. That was also co-written by George Clinton. So, he's still around. He's still doing good things. But this notion of UFOs and what this kind of like alien sightings, and he also did a lot of talking about, he does a lot of research about the Nation of Islam and Louis Farrakhan and like these visions that they say, religious visions based upon not just necessarily like a God or an Allah, but instead some sort of wheel that they saw in the air and there was alien beings inside. This notion that for historically oppressed people groups, very often the notion that there could be some kind of order beyond the current oppression that you're feeling can be a very rich physical balm, right? Both a psychological balm because it allows you to get through your day without, just killing yourself or something like, or giving up. But it also gives you a kind of psychological framework to view the world where you do have a reason to exist, and there is something beyond what is just your day-to-day physical world that you can aspire to, that there's someone in charge, things like that. So it's fascinating to hear about from that perspective too. And that's, that person is the guy who was studying that. He was not saying these are real, quote unquote, or not real. They're not physically real, but he's just saying that these are experiences that explain a lot of how different subsets of society have projected meaning onto the physical world, which I thought was fascinating. So yeah, I was happy to speak at the Sol Symposium. It's really interesting things.
Along the same grain is the idea, we have this drone problem where they're showing up over New Jersey, unexplained drones, and over the UK, and people are seeing them. And by the way, also photographing them, which plays into the UAP thing because we have a lot of pictures of these drones. It's real.
Yes.
Well, anyway.
Yes.
The thing is that if you took those drones, our really, really complex drone display, some of these amazing things that they do with swarms, show that to an uncontacted tribe on North Sentinel Island, it would spawn, imagine what they would think of that. They probably, to be honest with you, I have to give them the benefit of the doubt. They're probably like, oh look, it's the outside world. Look at it. They got lights.
Right.
And then they go back to hunting or whatever, and tending the fire. But at the same time, it might also spawn a religion, and it might go into it. Just imagine the uninitiated mind thinking through something that you see that you do not understand. And I leave open that that's what we're doing with the UAP, because it is not physically impossible for an alien civilization to be here. It would just be hard.
Yeah.
A von Neumann probe 3D printing out UFOs that are dipping into the atmosphere and people see them. And I leave that open. And I think it's prudent to leave that open. But the bottom line goes back to Missouri. Show me. And so far, nobody's shown me.
And yeah, I agree with you. I think that it's totally okay to keep this open as an idea, and I think it's more important. The framing would be, I guess, not to foreclose something. And honestly, science doesn't do that. So if somebody is thinking it's like, well, scientists are so close-minded. No, we're not at all. We're completely open to new ideas, and I think I've made it clear that I made it clear at the symposium too that I'm not a conservative scientist who only wants to study extremely known things and there's the kind of incremental changes. I mean, I published a paper proposing that we build a particle collider around the circumference of the moon next century, and I want to build a particle collider to make black holes around the sun sometime in the next 300 years or something like that. I love the edges of science, but it's okay for us to also ask for and require this kind of evidence. And it is not, we're not trying to be buzzkills. We're not trying to be downers. We're not dishonoring people's personal experiences when we do that. We're just making sure that we're staying true to the principles that have led science to be as successful as it is. Because the thing is that humans, one of the things that we love to do, we love to delude ourselves. We're extremely good at it. We're extremely good at assenting to the reality of something just because there's some kind of plausible pattern or some kind of emotional feeling we feel, and assenting, thinking that this is something real. And in some realms of human experience, that's totally, sufficient. Like, if someone said to me, it's like, you say your grandma loved you, but prove it to me. It's like, I don't have to design an experiment to prove that my grandma loved me. It's none of their business, right? However, if you're talking about the shared objective physical reality around us, then yes, we do have to prove that, because we have tricked ourselves many times in the past. And that's why, in a sense, that's why science exists the way it does, is that, among other things, I like to refer to science as our human way of reducing to negligible the human capacity for delusion. And if that's the case, that's what science has done. And so asking for and demanding this kind of evidence for it it's not untoward and it's not being extreme. It's just what needs to happen. No one's anti these things at all. No one should be anti UAP conferences. No one should be anti UFO thinking. Instead, we should just be pro evidence and pro very clear empirical understanding of something.
Be open-minded and show us what you got.
Exactly.
And I think that's the proper approach. And it seems that science is moving in that direction. It's moving away from the hardcore debunker and naysayer even to, all right, well, show us what can we get? What data can we get? And that's a much more healthy position.
And there was some really innovative ideas that I encountered at the symposium too. Somebody that was like, okay, well, one of the, again, I encourage people to look at my talk once it's finally online, but, as most people here probably know, a lot of what is reported for these UAP are physical behaviors, physical movements that just are not possible with human propulsion systems. And I say human just because that's all that we have, right? At least known human propulsion systems. So, and I go through a few of these in my talk too. And so you arrive at the conclusion that the only known physical set of phenomena that could account for, like I said, some 50-foot long tic-tac thing going from 80,000 feet down to 50 feet within 2 seconds would be some kind of warp drive that bends the fabric and manipulates the fabric of space and time. And this is a fun thought experiment to go through. Of course, we do not have warp drives. We're so far from understanding what warp drives are that it's really not, they don't exist. It is physically possible, but they don't exist. And so if that's the case, then my argument was that, to really understand it, kind of ties into what we were talking about earlier, to really understand whether this is possible, whether this could be a physically real object that was this enormous tic-tac. Again, we don't have any visual evidence of it anymore, just the eyewitness accounts. So if we wanted to prove it, then let's design one and let's build a warp drive. But to my mind, to understand how warp drives could possibly happen, these kinds of Alcubierre drives, and there've been some more recent work in the last, say, 10 years to put this on a more kind of physical possibility footing. We would need to understand quantum gravity, because basically a kind of warp drive style idea requires us to have a theory of gravity that is applicable and that is relevant and that is scalable down to small scales, which we currently don't have, which is exactly what we were talking about earlier with quantum gravity, right?
Quantum gravity and negative mass.
It comes back again.
God.
Oh yeah. negative energy density.
Yeah, exotic matter.
Yeah. Yeah, I mean, we do know of these concepts, and we have things like the Casimir effect, right? I mean, okay, these are real effects, but then the notion of harnessing these is so far beyond. Anyway, so it's very speculative, and I make that very clear in my talk. It's like when you start talking about warp drives, you immediately get into speculative territory. No scientist is saying they're real. We're doing the kind of the standard physicist thought experiment. What could possibly is it possible to make one of these? Are they physically impossible? Are there things that we haven't thought about to make them impossible? Blah blah blah. And I think that at the end of the day, we have to admit that there are certain things that are just unexplained and unknown right now. But obviously the notion of keeping an open mind, that's what science is. No one should foreclose these as a possibility. And I think that my main piece of advice, I think, to that realm, to the Sol, Foundation and the Sol Symposium people, is that one of the biggest problems that will keep coming up is that unless and until it is made very clear what are the kind of criteria for evidence for UAP, is that too often a lot of people, prominent people in the realm, it seems they're a lot more interested in storytelling and kind of selling books and things like that. And it's like, okay, whatever, get your bag, man. But like in terms of science, it really does a disservice because it makes it seem like things like the ET hypothesis or a supernatural phenomena or paranormal phenomena, these are somehow directly connected to the concept of unidentified aerial phenomena, which really does as a service because those other things, as we talked about earlier, they're not real.
Yeah, be very careful with that because, well, the thing is that, all right, it's hard enough with the UAP phenomenon to say this is all one thing.
Yeah.
Well, how do you know? How do you know it's not 10 things? And how do you know, for example, with the alien ET hypothesis, how do you know it's not a prior technological civilization from Earth? That's been brought up. So how do you know?
Yeah.
So you have to ask much, much broader questions from the outset, but it is the outset, meaning it's just started. Science is just now looking into this, but at the same time, there was an unfair stigma that was placed on the question because it never was implausible that there could be an alien in the atmosphere. That was never implausible. That can happen. A ghost? Well, that's a little bit of a different story, isn't it? That gets more into implausibility.
Sure, and I think I don't think we disagree too much. I try to go a little bit farther because so often these things get connected in a way that I think it tends toward the malevolent, right? I mean, so many of these things, because you say that it's possible that an alien civilization has been to our atmosphere. Okay, yeah, it is, but I can write down an almost infinite number of other possible things that are nearly undefinable or weird. And also, I don't have any evidence for this. Like, until and unless we can find some kind of direct evidence for an extraterrestrial civilization, the only data we have, and again, I'm the Missouri man, right? Show me. The only data point we have is us. The only thing we know about our universe right now is that at least one universe needs at least 13.8 billion years to evolve at least one species that can ask questions about the universe. That's it. That's all we have. And that's why I have to be very, for me, it's important to stay very stern about the notion that I cannot assent to the ET hypothesis as following from the concept of UAP. And that's just why and this will always come up. I'm not the only scientist that thinks this way. Other scientists, this is the kind of normal way to think about it from within mainstream science. And I'm not saying that mainstream is any better or worse than anything else, but like it's very well established. And so the reason I kind of belabor the point is that for me, it makes way more sense. It's not at all sexy compared to what people want to talk about, but it makes way more sense to say that people are scientifically interested in, or should be scientifically interested in UAP from the perspective of aviation safety. No one can complain about that, right? If there are things in the air, there's like, for example, these drone sightings over New Jersey, people should be rightfully alarmed. Where are those coming from? Who is doing that? What kind of asshole is sending 30 drones in, to over New Jersey? Like, what is going on here? And if there are unidentified things in our atmosphere that could potentially run into aircraft, that's bad. No one could possibly disagree with that. And then also the other part of that is where they possibly came from. Like I said, I don't think that the possibility of an ET civilization follows from that directly. We can speculate about that, but until we can see some sort of evidence from a SETI style thing, for me, that doesn't follow. The other part, though, is that maybe, and again, for me, I also find it a little bit implausible to think about past Earth civilizations that were technologically advanced. It seems like such a civilization would leave archaeological evidence that we would have been able to see so far. Maybe that's not for this discussion. That's for a different discussion.
Depends on how old it is.
True. Okay.
If it was 50,000 years ago, yes. If it was, I don't know, 68 million years ago, a smudge in a rock layer that may or may not be preserved. So
fair enough.
It depends on how old it is. And that was the point. And there were actually two papers on that. Adam Frank wrote one, called it the Silurian hypothesis, and Jason Wright wrote one and called it the prior technological civilization hypothesis, because Earth erases everything. And you're lucky to find a dinosaur fossil. You're lucky. It's just got to be exposed right where, in this certain location. But again, going back to Missouri being Missouri man, sort of like Florida man, Missouri man, is that we have no dinosaurs except for like one fossil somebody found on a mountaintop, because everything's gone. It wore away, washed away, and weathered away like the Ozark mountain range did. That used to look like the Rockies, and now it looks like Vermont, and it's gone. So you have this a function of time, and time being a very unfortunate thing. It weathers away, and Earth is just evil as far as weathering. It just incessantly weathers everything away. It's not beautiful like Mars or the moon, where it just sits there for billions of years. Everything on Earth gets destroyed. So you can play with that idea, but you can also play with ideas like, what's dark matter look like if you happen to catch it and see it? Is it a tesseract, like Carl Sagan once described in Cosmos? How would you know? How would your brain interpret something that you've never seen before and have no paradigm in which to understand? Therefore, you see it and you're like, what was that? So do you leave that open? And that's my last question for you. And the leprechaun in the tree is going to shock me with a taser, producer Ross, because we've gone over time.
I don't know. So if you're asking the question in the context of UAP, I've never seen one of these things. I've never been privy to a UFO sighting. And if you're talking about, and this is something that I was asked at the symposium too, because to be honest, I was the main sort of skeptic on stage, if you will. I call myself a benevolent, helpfully critical skeptic, not a kind of naysayer style skeptic. The truth is that it goes back to what we as humans are very, very good at, which is deluding ourselves. And that's true. Like we are just really, really good at this. And if I saw something that was so completely beyond all possible experience that I've ever had, my first thought is probably that I was hallucinating. And no, I'm not being dismissive of people's ideas, and I'm not avoiding the question. It's just that I know I know intellectually and rationally that humans do this. We do hallucinate. We do think about. We do, envision things that are just not real. So if I saw this and I saw imagine I was out in the desert by myself and I saw a big, flaming wheel. Let's imagine something very theatrical, and there were like sort of gray beans that came out of a staircase, and they said something in some language, and then they went back up to me, and then I went back. Honestly, I would not try to convince other people that I saw that, not from a stigma perspective, but because I don't have any evidence for it. If I didn't take any photos, I didn't take any video, there's no reason for them to think that anything that I was saying was corresponded to reality. And also, we do know that humans, we delude things. We have hallucinations. And I know that some people, listening to this that may have had experiences will think that's me being dismissive, and that's not what I'm trying to do. It's just like I said before, if you see something that's it goes so far beyond what we currently understand, the way the universe works, the way that physical reality works, your first thought should not be that all our complete understanding of physical reality is wrong. Your first thought should be, how does this fit in with our current understanding? Because, one of the things that we talked about earlier, these paradigm shifts, things like that. Keep in mind that in the history of physics, we talked about, say, the transition from Newton to Einstein. When Einstein came along, it doesn't mean that Newton was wrong. In fact, Newton was completely right, up to and including the scale at which he's applicable. But beyond that, and in fact, for most of the calculations, if you want to do calculations about big calculations, simple ones about the solar system or various things, you can use Newton for most things. However, if you want to get the nitty gritty and the details right, then you have to move to a totally different, paradigm, which is general relativity. That doesn't mean that Newton's wrong. It means that something came along to better explain more things. And if that's the case, then, I also think that's the case for something that I didn't fully see at the time, or I didn't fully understand when I experienced it. I don't know if that answers your question, but that's the way I think about those kinds of things.
Newton will get you to the moon, but just not in the exact place you thought. that you're going to need general relativity for. All right, James, it was a pleasure talking to you as always, and I wish you good luck at CERN, and make me a black hole, a micro black hole. Just make one. Alter the laws of physics, make one, or build a collider the size of the solar system to do it. But yeah, I would definitely find the existence of a black hole would be amazing. And when we're talking about dark matter, maybe those tiny black holes are everywhere, and we just need to capture one.
Ooh. That sounds like a totally different episode where we talk only about the different paradigms of dark matter, primordial black holes,
and WIMPs. I'm stuck on WIMPs because of neutrinos. A neutrino is a WIMP, and I'm like, well, maybe you could have another type, perhaps. Anyway, we'll do that next time. Yeah,
my pleasure.
Event Horizon and my channel are now available as a podcast on Apple Podcasts, Spotify, and YouTube memberships. Early ad-free episodes, bonus episodes, and sleep-focused content. Sign up now by clicking the links below to your platform of choice.